Okay, next we have the true story of my wife and myself in Paris for New Year's Eve, New Year's 2011. Uh, my wife is awesome. What can I say? She just found us this great package deal, whatever, chance to go to Paris. We did it. We celebrated New Year's Eve under the Eiffel Tower. It was really awesome. Okay, but anyway, so I did actually see this thing. It was a merry-go-round, but it was slanted, so or tilted. So it rotated about this axis, but it was tilted, and the whole thing was tilted. So it was like you were on a flat merry-go-round that just the whole thing had been picked up and turned some angle, which I guess we're saying here is 30 degrees, and I don't remember exactly, but sure, let's call it about 30 degrees. Okay, so what we want to do here is say what happens. So a child riding at the outer edge, he's 1 meter away from the outside, or from the center, right? Okay, so actually let me actually use the line tool now that I know how to use it, and I'm just going to draw like a side view of the thing, and let's go one side thicker. Okay, so let's say here is a child at the upper outside edge, here's a child at the lower outside edge. Okay, and this is a 30-degree angle. I wonder if I like it that thick. Yeah, maybe we'll see. Okay, so which child is in more danger of falling off? Let me back up a little and say the point is right here. I'm trying to figure out at what point on this circle of the ride is the child most likely to fall off. So where is he going to be closest to slipping off the edge? Okay, so I'm surmising that will be at either the top or the bottom. Okay, and let's see how well that works out. So at the top, of course, you've got gravity acting on him, and you've got normal force. Okay, same deal at the bottom. Okay, now in both cases, he needs to accelerate inward, right? He needs to accelerate towards the center of the merry-go-round. Okay, so and that means he is accelerating on a slant. We're used to these circular motion problems having you accelerate horizontally, since we've done horizontal circular motion before, but he is actually accelerating towards the center, and since his whole circular path is slanted from horizontal, that means his acceleration is slanted from horizontal as well. So there's the acceleration he has at each of those points towards the center of the merry-go-round. And which way does friction act at each of these points? Well, here you could see it acting either way because there's already a component of gravity that's pointing inward, right? So possibly friction could be acting outward, possibly could be acting inward. On the other hand, right here, there is no force acting inward. So he has to have friction there, okay? Which means this spot down here, this is what we're going to call the critical point. Critical, okay? And this is where he is most likely to fall off, because this is where friction is going to have to, put out the most mojo, okay? So this is the one we're going to do, okay? So I'm going to come over here and do a free body diagram of the kid at that point on the left, but let me just make sure that's normal. That's the kid's mass times g, and that's the force of friction, okay? So now over here, okay, here is the normal. Here is the force of friction, and here is gravity. And the angle here is theta, which is 30 degrees. Theta, so I'll just name it over here. Theta equals 30 degrees. Okay, what coordinate axis are we going to use to break this down? Well, we are going in circular motion, which means we are accelerating towards the center, which means it has to go in that direction. Like I said, technically, you could, but man, you do not want to, okay? So let's do it like that. And, well, what the hell? Since I've already drawn it this way, let's put x going to the left, which is, I know is wacky, okay, but we're just going to do it. Okay, and y going up, of course. So now I'm going to have force of friction is there. We have the normal force there. We're going to have mg cos theta that way. And down here we're going to have mg sine theta. Okay? So, yep, and you should be able to break down, angles like this easily by now. We've done enough of it. Okay, sum of forces equals ma. We which means in the x direction. And this is where I got to be tricky because I did my x going uphill to the left, so that's kind of strange. But friction force minus mg sine theta equals m times your acceleration in the x direction. Okay, y direction, normal minus mg cos theta equals m times acceleration in the y direction. We know that's 0. What about acceleration in the x direction? Well, he's going around this merry-go-round, which has an angular velocity omega, and he is riding at the outer edge of the platform and has 2 meters diameter, which means the radius of it is 1.0 meters, or 1.00 meters. Okay, so now his acceleration his centripetal acceleration has to be omega squared r. Okay, so now, now we're getting somewhere, right? And that's our ax here, because that's what's going towards the center of the circle here at this point. So this is going to be m omega squared r. Okay, so let's see. Let's solve this puppy. Switching to purple just because I like purple, and let's do purple. I mean, I want to do dark colors, right? I don't want to do something that's not going to be readable. So we can take this guy, solve it, and get that the normal force equals mg cosine theta. Okay, and we know of course that the friction force is coefficient of static friction times the normal force, which is going to be coefficient of static friction times mg cos theta. Okay, and so let's see now. We take that then and plug it into this equation. Here's our FF, right? So we take that and plug it in there, and we're going to get mu s mg cos theta, that's our FF there, minus mg sine theta equals m omega squared r. Okay, so we're going to cancel the m's. Let's see, let's go with that baby blue there. Oh, that's kind of cute. Okay, cancel the m's. Okay, and then we want to solve for, what are we solving for? The greatest possible angular velocity. So we want to solve for omega, right? So let's take this and go, we can take omega to the left-hand side. So we go omega squared r equals, and then we can pull the g out, right? And then go mu s cos theta minus sine theta. Okay, and then let's just page down a wee tad. I'll solve for omega, and so you go there. Omega equals g over r. Actually, this is omega squared. Sorry, omega squared is g over r times mu s cos theta minus sine theta. And then, of course, we want to get rid of the omega squared. We just square root the other side, and then there we go. Cha-ching! Poosh. Okay, so let's see really fast what this is. What do we say? It's 0.650 for mu s. So 0.65 for mu s times cosine of 30 degrees, which is that root 3 over 2 thing. What's z 30 degrees? Okay, cosine 30 degrees.